Hi, my name is Logan, and today I'd like to talk to you about Bayes' theorem. It is the key to understanding conditional probability. Basically, Bayes' theorem is a way to revise existing predictions based on new information. So to understand Bayes' theorem, we're going to follow this approach. First, I'm going to describe the theorem to you. Then I'm going to describe to you why it's important by highlighting a few use cases. Then I'm going to help you understand how to use the theorem by walking you through a guided example. And then finally, you'll see the power of the theorem when it's implemented with code. And with this code, I'm using Python. So here's the theorem up at the top. As you can see, it's composed of two variables, A and B, and A and B represent events. This vertical bar here represents given. So this whole equation here, or this whole portion of the equation, means the probability of A given B, and the jargon term is posterior. Then going down, this would be the probability of B given A, and then this is the probability of A in isolation of B or independent of B, and then this is the probability of B independent of A. So that's kind of a lot, and it's probably, if you're unfamiliar with this, a bit confusing, but hopefully it'll make more sense when we go through the example together. First, though, I'd like to just give you an idea of why this is such a useful theorem with a few use cases. So I'm just highlighting three different industries here, but this theorem's applied all over the place. The first example I have is in finance. You can use this theorem to evaluate the risk of lending money to potential borrowers. So the example might be you can evaluate a certain person will have a certain likelihood of defaulting on a loan. If you get new information about this person, it might color your existing prediction. So you should update your prediction based on information you're getting about this individual. One kind of very famous example in medicine, this is used to determine the accuracy of medical tests. And we're going to be going through an example together shortly on this. So I'll just leave it at that. And then in AI, or artificial intelligence, people use this theorem to model machine beliefs. So basically, it's a model of what the computer is thinking at a given moment. So our guided example is the mammogram problem. So here is kind of some facts we're given. So the probability that a woman in her 40s with breast cancer will get a true positive result on a mammogram test is 90%. And then the probability that a woman in her 40s without breast cancer will get a false positive result on a mammogram is 7%. And then the last fact we're given is, of all women in their 40s, a little less than 1%, 0.8, will develop breast cancer. If a woman in her 40s gets a positive result on a mammogram, how worried should she be? So we're going to take these facts and plug them into the equation, and we'll get an idea of really how worried a woman should be if she's in her 40s and gets a positive result on a mammogram. And the result of this equation will maybe make you question the value of mammograms. So let's go take a look. So plugging it in, we get on the left-hand side of the equation, the probability of cancer given a positive result. And this is what we're looking for. So plugging in the right-hand side, we get the probability of cancer multiplied by the probability of a positive result given cancer already exists, already divided by, or excuse me, all divided by the probability of a positive result. So one very useful tool I found in plugging in these numbers was to kind of examine this in like a little node diagram. So I have that here. So the way this is laid out is you kind of start on, I'll say you start on a journey basically. So you either go, you have cancer, and then there's a likelihood of a positive or negative result from the mammogram. So this is kind of one likelihood or one probability journey. You could go down this way, or you can go down not having cancer, so not C, and then the likelihood of a positive result, and then the likelihood of a negative result. So as you can see, there's basically 4 total outcomes, 2 of which will be positive, and then 2 of which will be negative. And then you can see these numbers here, and that kind of helps explain how to plug it in. So on the right over here, you see the probability of cancer is pretty low. It's right there. The probability of a positive result given cancer is this number, and hopefully you could kind of see that connection there. And then the bottom is the probability of a positive result for everything. So you basically go down 2 journeys here. So you're going to add 2 probabilities together. You add this journey here, and then this journey here. So these 2 numbers are multiplied together, and same with these. When you plug all that in, you get 9.4%. So that's the likelihood that a woman has cancer given a positive result. So this kind of shows you or gives you a good idea of the accuracy of mammogram tests, the true accuracy of mammogram tests. Lastly, we're going to do an implementation with Python code. So you're going to see how cool and how useful this theorem is when it's applied with some code. So this is slightly different than the mammogram problem we just discussed. That was kind of just based on like one instance of something. So like one instance of something that's based on a prior event. So the prior event would be whether or not the woman had cancer. In this example, we're constantly updating our prediction of something. So once I describe this to you, it'll give you a better idea, I think. So this problem is you have a bag containing equal numbers of 3 different kinds of dice. Each die has a different probability of coming up 6 when rolled. Their respective probabilities for coming up 6 are listed below. So some gamblers, as you might know, use weighted dice. So these die have different probabilities for coming up 6, and you can see them right here. Now the problem is, if you reach into the bag and pull out 1 die, it is not hard to figure out that you have a 1/3 chance of having pulled out a die of type A, because they're all in equal numbers. Now imagine that you roll the die twice and it comes up 6 both times. Having observed the die's behavior, how much more likely is it that it is a type A die? So basically you're revising your prediction. So if you pull it out and you don't roll it, you have a 1/3 chance of it being type A. But if you roll it twice and it comes up 6 both times, and a type A die is more likely to do that, just how likely is it that you pull the type A die? So we're going to take a look at some code, and it'll give us the answer to this problem. Okay, so here's the little program I wrote to demonstrate Bayes' theorem. So this is Python code. I don't think I need to explain every line of the code for you guys to understand what it's doing, mainly because I think that'd kind of be boring for everybody. But I'll quickly go over it so you get a general idea. So at the top, I wrote kind of just a basic function. So it takes 3 parameters. It takes the prior likelihood of drawing a type A die. And as we discussed, that's 1/3 because there's 3 types of die. Then the second parameter, it takes the likelihood of rolling 6 if you have a type A die. And then the third parameter is the probability of rolling a 6 overall, which is all of their respective probabilities divided by 3. And then the code down here, I basically kind of wrote a simple like looping menu style game where the user can choose to continue rolling or not. And yeah, let me give it a go and you'll see how it works. So the game starts out assuming the user has rolled. So then it asks if they rolled a 6, we'll say yes. And then we learn that the probability of having a type A die is now 39%. Because it started out as 1/3, and having rolled a 6 and knowing that type A die is more likely to do that, it's now been updated to 39%. And if you roll again, and you roll a 6 again, we now see that it's even higher. It's 46% likely that you have a type A die. And that makes sense, right? Because a type A die is likely to roll a 6, and if you keep rolling 6s, it becomes more likely, you feel more confident that you have a type A die, right? And the way this code works is this prior A figure, this kind of prediction that we have a type A die, is continuously being updated each time you roll. So new information is kind of coloring our prediction on whether or not we have a type A die. So I kind of hope that you guys got a good understanding of how this theorem works. I hope you kind of maybe think it's interesting or see its value and its use in making predictions. And hopefully you guys learned something from this presentation. So thank you for your attention.